Okay, kids, so we're back again today, still talking about energy. And we learned last time that energy is given to an object or taken away from an object if work is done to it. That is, if a force is applied to it through some displacement. So what we want to do today is take a look at some particular types of energy that are very common when we study the motion of objects. And one of those energies is called gravitational potential energy. Its symbol is Eg or EP, depending on the textbook. What is this energy? Well, it's the energy due to an object's mass and its position in a gravitational field. And I think you've all experienced this in your lives. If you ever had something fall on your foot or on your head, what have you, if things fall on you, they can hurt. You can get a boo-boo. So they had some energy in them so that they were able to do a work. They did a real job on your hand if, or your foot if it landed on you. Anytime an object has a height and a mass and it exists in a gravitational field, it has the potential, as it falls and lands on something, to do work on the object that it lands upon. So we know it had energy in it. So let's do an example here. Let's say here's an object, it's green. Here's this object right here, and I'm going to lift it upward with a force F. I'm just going to call it F. And while it's being lifted into the air, we know that there's a force of gravity, a weight acting on it, and it's the mass of the object times the gravitational field strength. So it's going to be working downward, or operating downward, I should say. So here are the two forces acting on this object. And let's say we start the object right down here, and then we lift it upward. And we lift it upward so that it's not speeding up, it's not slowing down, it's just moving upward at a constant velocity. And then somewhere up here we'll stop. We're going to be interested in the object's motion between here, little purple line here, and here, purple line right there. And we're going to say that in this area right here, it was definitely not speeding up, not slowing down. It had an acceleration equal to 0. And we're going to say that it had a change in position or displacement delta D. And since the height is changing, we're going to call this delta D a very special type of change of displacement. We're going to call it delta H. Just changing the symbols for convenience sake. And this is all happening at a constant velocity, 0 acceleration, while we are near the surface of the Earth, so there is a gravitational field acting on the object. Now, let's see the consequences of having an acceleration equal to 0. Here's an equation that has acceleration in it. F net equals ma, the most important equation in physics. But the acceleration is 0, which means if I put a 0 in here, the net force is 0. That's very important because we can then rewrite F net in its other style, its other manner, its other definition. F net is equal to the sum of all forces acting on an object. So here it is right here. Here are the two forces acting on the object as it's being lifted into the air. There's force F, there it is, so I wrote it down, and there's the force of gravity on it, there it is, so I wrote it down. And these two added together have to equal 0 because the acceleration is 0. So I bring force of gravity over to the other side, and it becomes negative. So the consequence of having an acceleration equal to 0 during this motion is that the force that's lifting the object has to be equal in magnitude, but opposite in direction. Look, we got the negative sign there, but opposite in direction to the force of gravity. All right, let's continue now. All right, yeah, we're going to continue, and we're going to remind ourselves that we can calculate the work done on an object by a force, so it's a scalar here. The work done by a force, in this case it's force F, okay, is equal to that force dot product the displacement. But since this is a very special displacement, it's being pulled straight upward. Instead of using delta D, we're going to use delta H. What's the recipe for dot product? Well, it's the magnitude of the force times the magnitude of the displacement times the cosine of the angle between them. Well, kids, the change in displacement, delta H, and the force lifting the object, F, are both straight upward. They're parallel to each other. So the angle between them is 0. And the cosine of 0 is 1. So I can rewrite it as magnitude of the force, magnitude of the displacement times 1. The other thing I want to remind you of is we just worked on this, that the force acting to lift the object is equal in magnitude but opposite in direction to the force of gravity. So I'm going to rewrite that as negative Fg. I'm taking advantage of the work we did here, taking advantage of that and using it in here. Now, since they're all in magnitude signs, let's just put them all in a magnitude sign together. So we have magnitude minus force of gravity times the displacement and magnitude. Next thing we're going to do is remember that work is equal to change in energy. That's one of the things we learned in our last lesson, that work is equal to change in energy. But in this case, it's a very specific type of energy that we're changing. We're changing the gravitational potential energy of the object because we're lifting it upward. We're giving it height. So I can come up with a brand new line here and say that the change in the object's gravitational potential energy, right here, is equal to the work done by that force, and it is also equal to the magnitude of negative, because you have a negative sign here, mg, mass of the object, times the gravitational field strength. Why? Because I know that's the equation for the force of gravity. See it right here? We've used it many times. So I'm going to put that in times this height displacement, delta H. Now, since this whole term, mg delta H, since this whole term is within magnitude signs, I'm going to drop the negative sign and I'm going to drop the vector signs because I'm only interested in the size. I'm only interested in the magnitude. So I can rewrite it just like that. There you have it. Well, we have to remember what delta means. We have to remember what delta means. In this case, delta gravitational potential energy is gravitational potential energy at the final position as we were lifting it minus the gravitational potential energy at the initial position as we were lifting it. And that's going to equal mg delta H. So I'm going to rewrite this here. See how I'm rewriting it? Just write it again. Is equal to mg. Rewrite the m, rewrite the g. But what does delta mean? Well, we've used delta many times. Delta means height final, delta h, height final minus height initial. And then I'm going to do some distributive multiplication in. I'm going to bring the mg onto the height final. I get mg height final. I'm going to bring the mg, multiply it into the negative height initial. I get negative mg height initial. So now on each side of this equal sign, I have a subtraction going on. I have a difference. So that means the first term here has to equal the first term here. They're in red. The second term here has to equal the second term here. They're in blue. So what I've actually discovered is a general equation that we can use all the time now, and it is as follows. If you ever want to know the gravitational potential energy of an object, it is equal to the mass of the object in kilograms, the scalar version of the gravitational field strength. Notice there's no vector sign here, so this is just 9.8 newtons per kilogram. There's no negative sign in there, don't need a direction, times whatever height it has. No direction, no positives, no negatives, just the magnitude. Here is another equation we can put into our equation sheet, the equation for the gravitational potential energy of an object. All right, let's do an example. How much work does Mr. Z do when he jumps 20 centimeters into the air? So let's draw a little picture of what's happening here. Here's a picture of myself. There I am. Okay, and I'm on the ground. So my height is equal to uh, 0 to begin with. And let's assume that I'm just going to have a little bit of acceleration at the beginning. We can ignore that. A little bit of acceleration at the end. Okay, there. And we can jump straight up in the air. Let's say there's very little change in speed along here, not much change. Okay, and I jump up into the air. Okay, and as I jump up into the air, we have a height increase of 20 centimeters. So very short amount of distance. Okay, not much happening here. Okay, so the work that we do is equal to uh, E delta EG. Work is equal to change in gravitational potential energy. All right, and that is equal to gravitational potential energy final minus gravitational potential energy initial, which is mg height final minus mg height initial. All right, so we put in the mass here. We put in 9.8 newtons per kilogram here, but it's not negative. It's just the scalar part of it times 20 centimeters minus, well, I put 0 here because my height initial is 0, so that whole term is gone. And then I get 67 kilograms times 9.8 newtons per kilogram. Notice there's no sign here, just the scalar version. 20 centimeters I can't use. I got to turn that into 0.2 meters. And then here's how much work was done as the gravitational potential energy changed. You just multiply these. Another way of doing it is here in the green. Mg height final minus mg height initial is equal to mg factored out of each term, and we have height final minus height initial. So then we'd have 67 kilograms times the 9.8 newtons per kilogram. Notice there's no negative here. And then we subtract the two heights. It's two different ways of doing it, but you get the same answer. Okay, kids, we're back again here. And the second type of energy that's really important when we study motion is kinetic energy. All right, AEK is the symbol. It's defined as the energy of motion, the energy of motion. All right, so it depends on the mass of the object and its speed. So once again, let's do a little experiment here in our minds. Let's say there's this object right here, and it's not moving. Its initial velocity is 0, and a force is applied upon it, and that force operates on that object through a displacement I'm going to call delta D. Through a displacement I'm going to call delta D. So that at the end of its motion, it's no longer not moving. It now has some final velocity. It's been accelerated. It's been sped up to this new velocity, which we're going to call velocity final. All right. Now, let's, for the sake of argument, say that this force right here, is the only force acting on the object. So since it's the only force acting on the object, it by default becomes the net force, because you just add up all the forces, and if there's only one acting on it, then that one there is the net force. So keeping things really simple here. Only one force acting on this object right there. So let's take a look at this from a kinematics point of view. And we're going to write out this kinematics equation right here. Final velocity squared is equal to initial velocity squared plus 2 times the product of the acceleration and the displacement. Well, the initial velocity was 0, so that term is gone. So all that we have left is 2 times the product of the acceleration times the displacement. There you have it. I've rewritten it there with that 0 taken into account. Now I'm going to divide each side by 2. Here's a new line. I've divided each side by 2, so there's your new line. And now what I'm going to do is I'm going to say, look, if the direction and the magnitude are equal, let's just focus in on the magnitude. So that's what I'm going to do. Wherever there's a vector, I'm going to say take the magnitude of that vector alone. Wherever there's vectors, I'm going to say take the magnitude of the vectors alone. Because if it's true, this equality for both direction and magnitude, it's going to be true for magnitude all on its own. And then I rewrite it just like that. Notice there's no vector signs. I'm only interested in this equality between the magnitudes. Now keep this in your back pocket. We're going to return to this. All right. Now remember, this unit is about work and energy. And in this particular situation, we're talking about the energy of motion when an object is moving, its kinetic energy. So let's take a look at the work done by this force right here. So the work done by this force would be the force dot product the displacement right here. There's the force, there's a displacement. Find the dot product between them and you will have calculated the work. Now that work is equal to, because we know what dot product means, the magnitude of the force times the magnitude of the displacement times the cosine of the angle between these two vectors. Well, kids, they're both pointing in the same direction. Look at that displacement vector. Look at that force vector. They're parallel. So the angle between them is 0. So cosine of 0 right there. And cosine of 0 is 1. Cosine of 0 is 1. So I can replace cos theta with the 1. And we have this line right here. Magnitude of the force, magnitude of the displacement times 1. Well, let's continue. A while ago, I told you that since it was the only force, it becomes the net force. It's the only one there. F net equals the sum of all forces. It's the only force there. So it is F net. And we still have the magnitude of the displacement, and there's no need to write the 1. Now we use the fact that we know Newton's second law, and we rewrite F net as mass of the object times its acceleration. I replace it with this expression. And we still have the magnitude of the displacement. Now, since it's all in magnitude signs, all right, I can drop the magnitude signs and just write ma delta d. No vector signs. I'm only interested in the magnitude. Now, what's very interesting is we've seen this term acceleration times displacement. We've seen that before. Look, saw it right over here in the previous work that we did. So where we have acceleration times displacement, let's replace it with the speed final squared divided by 2. And that's what I did in the next line. The m stays the same, but instead of writing a delta d, right, let's replace it with something it's equal to. Speed squared, the final speed squared divided by 2. There it is. I've done the replacing. The next thing we have to remember as we move on to the next line is the following. That if you do work on an object, you change the object's energy. In this case, we're not lifting the object up into the air, we're speeding it up. So we've changed the energy of motion of this object. We've changed its kinetic energy. That's why I've replaced the W, work, with change in kinetic energy. So change in kinetic energy is equal to the mass of the object, the final speed squared, all over 2. But now please remember what delta change in kinetic energy means. It means kinetic energy final minus kinetic energy initial. That's what delta means. The final situation minus the initial situation. We've seen that many times. I'm going to rewrite this term right here. I'm going to rewrite this term right there. Mass times final speed squared all over 2. And I'm going to say subtract 0. That may seem odd, subtracting 0, because if you subtract 0, you've not done anything to it. But it's a little trick we can use here. Because I'm going to replace 0 with an expression that is equal to 0. Mass of the object times its initial speed squared, all divided by 2. This is also equal to 0. Oops, this is also equal to 0 because the initial velocity was 0. So there would be a 0 in here anyways. I'm not changing the value. I'm just expressing 0 in a different way. Why am I doing that? because I want to set up differences on each side of the equation. I want to set up differences on each side of the equation. And that will allow me to say that if I'm subtracting these two here and I'm subtracting these two here, then the first terms must be equal. I've connected them with this yellow line. And the second terms must be equal. I've connected them with this red line. So that means I have now come up with a general equation for kinetic energy. We can put these equations in our equation sheet, that the kinetic energy of an object is equal to the mass of that object times how fast it's going squared divided by 2. Or if you don't want to use divide by 2, it is half of mass times speed squared. Either way is fine. All right. Here we are. All right, let's do an example. How much work is done to accelerate a car of 1,000 kilograms from 15 meters per second positive, there's its initial velocity, to 20 meters per second. There's its final velocity, 15 meters per second to 20 meters per second. How much work is done? Well, work is equal to change in energy. But in this case, we're not lifting the object up into the air, right? We're not changing its gravitational potential energy, we're changing its kinetic energy. So in this particular case, work is a change in kinetic energy. Change in kinetic energy means kinetic energy final minus kinetic energy initial. And that is half the mass final speed squared minus half the mass initial speed squared. Notice I'm calling it speed now. There's no vector signs here. I don't need these positives, just the magnitude. So that is equal to half times 1,000 kilograms times 20 meters per second squared. Look, I didn't put positive 20 meters in here. I just put 20 meters because it's a scalar. Oop, made a little boo-boo there. Let me fix that. That's not a plus sign. That's a minus sign. Let me fix that right now. Silly Mr. Zafiro. There we go. And then we repeat half the mass times the initial speed squared. I'm saying that on purpose here. It's not a vector here. It's just the magnitude of the velocity, also known as speed. All right? And then we do our mathematics, and we get 8.8 times 10 to the 4 joules. It's very important you realize that work and energy are scalars, right? So this is not final velocity squared, it's final speed squared. Initial speed squared. Very important you remember that. So I'm going to give you some other cartoon videos to watch. There's a note. Give you some homework questions. Try them if you need help. I'll help you. And have a great day.